In this video, I will explain you Maxwell's equation. So these four are Maxwell's equation, but you know that these equations are not discovered by Maxwell's. Gauss's theorem in electricity by Gauss, this one is by Gauss, and this one by Faraday, this one by Ampere's. Now why these four equations together it is named as Maxwell's equation? Because when Maxwell came, he has completed basically equations, Ampere's circuital theorem, and after that with these four equations he has proven that the entire electromagnetism can be explained with these four equations. This is just enough to complete the whole electromagnetism. See, till Ampere everything was fine, but Ampere hasn't given here, so this is insufficient. But Maxwell has came and completed the thing. So once he has completed, then we can say the whole electromagnetism is explained. So with these four equations, the whole electromagnetism can be explained. Now we will see one law after other. First theorem is Gauss's theorem in electricity. Simply take a charge, cover it by a Gaussian surface. There shouldn't be any hole. If a hole is there, we can't apply it. Cover it completely, then the total flux passing through the Gaussian surface is equal to, this is the total flux, that is equal to 1 by epsilon 0 times charge enclosed by this. Now if the total charge is, let's say plus q I have kept and minus q I have kept. Now if I am drawing a surface in this way, the total charge here inside the Gaussian surface is 0. See, plus q and minus q, sum. What is the sum? 0. So here q will become 0 and the entire term will become 0. Okay, now this concept is the foundation for this thing. Gauss's theorem in magnetism. Now in magnetism also we can keep a magnet inside. Here as we have played with charges, here we will keep a magnet inside a Gaussian surface. Now we know that associated with any magnetic field or any magnet, there will be two poles, a north pole and a south pole. So in magnetism, magnetic monopole doesn't exist. So we have a north pole and we have south pole. From north, field lines will be coming, to south it will be terminating. So 3 going out, 3 coming back. What is it? 0. So as there are two poles, dipole here, then it can be treated as a case like this, equal and opposite poles. Okay, now this will become 0 because total magnetic field out is equal to total number of magnetic field lines in. Now Faraday's law of electromagnetic induction, we have learned that the reason for induced EMF or a voltage in a circuit which is kept in time varying magnetic field is nothing but the change in magnetic flux associated with the link. So when we have a coil and this is connected to ammeter, now when we are taking a magnet towards it and away from it, we will see a deflection in this galvanometer, which means there is a current here. Who has produced a current? An EMF has produced a current. And what was the reason for the current here? The reason was change in magnetic flux. It's magnetic flux, not electric flux. Magnetic flux associated with this coil or linked with this coil. Okay. Now, according to Ampere's Maxwell law, it is covering Ampere's circuital theorem first, that is mu 0 IC, and he has added an additional term, that is mu 0 into ID. So mu 0 into IC, this is nothing but mu 0 into total current, which is IC plus ID. That is, we will have conduction current and displacement current as well. Now as we know that current produces a magnetic field here, we have learned a very important things here. It's always current that produces magnetic field, but it is not only movement of charges. Now here IC means IC will only happen due to movement of charges. Movement of charges has produced a current here, but we have learned that displacement current also will be producing a magnetic field in the space. And what is the reason for displacement current? That is change in electric field. This is very important for this chapter. See, movement of charges is conduction current, that will produce a magnetic field. But along with that, see here in this term, can you see any movement of charges? No. But if this term is 0, if this is there, that can also produce magnetic field. And in this term you have change in electric field, which means when we are taking two capacitor, we are charging the capacitor, electric field is increasing. Now this change in electric field can produce a magnetic field. Now here, change in magnetic field can produce an electric field. See, voltage, we have learned V is equal to E into D. So E dot dr, minus it is actually. Now this EMF can be written as minus E dot dr. We have learned it, right? dV by dr is equal to electric field. We have learned this equation. Minus dV by dr is equal to electric field. Okay, so this is equal to dV is equal to electric field into dr. This we have learned initially. Now I can say that E dot dr is equal to E, that is induced EMF, that is equal to d phi by dt. See, change in magnetic flux or magnetic field creates an electric field here. Now change in electric field creates a magnetic field. So both change in electric field can produce a magnetic field and change in magnetic field can produce an electric field. This is very important. Okay, thank you.